Okay, so this is the MOSFET common source amplifier circuit. Okay, so exactly similar to the JFET amplifier circuit. Only the difference is instead of a JFET, we have connected MOSFET here. Okay, and the same MOSFET we are using, that is 2N7000, which is a N channel enhancement type MOSFET. Okay, for this experiment. The same MOSFET we have used for a earlier experiment also, that is MOSFET as a switch. Okay, and you can now identify which biasing scheme we are using, which amplifier configuration. Okay, it is that much study already we have completed. Okay, so the same biasing technique, same type of amplifier configuration or topologies we are studying for different types of transistors. Okay, so you can identify here we have RG1 and RG2, which consists of our voltage divider biasing scheme. Okay, so very easily just by looking at the circuit we can know this is a voltage divider biasing scheme. Okay, and here we can see the source terminal is common in between a gate and the drain. Yeah, input we are connecting to the gate terminal, and output we are taking from the drain terminal of the MOSFET. So it is a common source amplifier topology or the configuration. Okay. Rest components are we have a drain resistance, we have also a source resistance connected, we have a bypass capacitance. Okay, all of you know the significance of bypass capacitance, clear? So what will happen during the EC circuit? Okay, so it will bypass our source resistance because source resistance decreases the gain, okay, gain of the amplifier, and that is unwanted thing. So we have to bypass the source resistor, clear, during the application of the AC input signal. Okay, so that gain should not be degraded. So this CS will play that role. It will bypass the source resistor during the AC input application. Okay, and these are the coupling capacitors C1 and C2. So in every amplifier configuration, whether it is a BJT amplifier or JFET amplifier or a MOSFET amplifier, we are having these coupling capacitor and bypass capacitor. Okay, so this is the simple common source MOSFET amplifier. Okay. And just we can find out how much gain we are getting. Input we are applying very small input. One you can see here. Let me start its properties. Okay. So we are applying 1 millivolt peak amplitude signal, yes, sinusoidal signal of amplitude 1 millivolt, frequency 1 kilohertz. That means a low frequency, clear. EC analysis magnitude 1 volt. If we are plotting AC response, then we must set the AC magnitude also, and that I already told you, we set 1 volt so that whatever V out we are getting, output voltage we are getting, that itself is equal to the gain, clear? Because that will divided by 1 volt is nothing but the, so gain and V out will be equal if we are input AC magnitude is 1 volt. That's why we set AC magnitude 1 volt. Okay. So these are the input signal parameters which we set. The same parameters we set for earlier amplifier experiments also. Okay. Okay. So now just by simulation we can find out how much output voltage amplitude we are getting. Clear? So by running a transient analysis, we can plot V in and V out, and we can observe the amplification of the input signal. Clear? Also, we can measure how much output voltage you are getting. Clear? And just divide output voltage amplitude by input voltage amplitude, and you will know the gain of the amplifier. Okay, so that is one of the methods. By transient analysis we can know the gain. Also by running AC analysis, that is by plotting the AC response, magnitude response, also we can know how much gain we are getting. Clear? So we all know that already we have performed the transient analysis to find out the magnitude, amplitude, and then gain, as well as we have in earlier experiments we have performed the AC analysis also. Clear? To find out the V out magnitude and that equal to the gain. That itself is a gain. Okay. So you can find out the gain by any way, by running a transient or by running the AC analysis. Also, if you don't want to go for analysis, so what you can do, you can connect the CRO also, oscilloscope. Clear? This way you can connect CRO also, and you can observe the input and output signal on the oscilloscope and find out the amplitude and find out the gain also. So that option is also available. So it's up to you how you want to do it. Okay. So you can connect the CR also. That's not a problem. Okay. So I will prefer the transient analysis. So I will go for a transient analysis. Okay. So these are the transient analysis parameters. Okay. So I'm starting start time 0.02. Clear? So 0.02 seconds. So this will be the 120 millisecond. I'm starting. End time 25 millisecond. Okay. Should never start the transient analysis at a zero time, because transient response required a settling time. Signal has to be settled. It will become stable after some time duration only. Okay. So that's why always take this precaution. Always start the transient analysis somewhat later time, not at a zero time. Okay. Start time, don't take a zero. Otherwise, you will not get a stable signal at the in the simulation. Okay. And output, so input and output, these two signals, voltage at the input and voltage at the output, these two signals I want to observe. Okay, so that's why I have added these two signals, okay, into this selected variable list, and I will go for run. So you can see here, there. So the green one is my the output signal, amplified signal, and red one is which is a very small compared to the output. That's why it's looking like a DC signal, but it's not a DC signal actually. Clear? It's having already we set its amplitude to the 1 millivolt. Okay, so it's a peak to peak 2 millivolt. Red signal is having a peak to peak 2 millivolt peak to peak amplitude. Okay, but why it is looking like this? Because compared to this output, this is very small. That's why it is. It seems like a DC, but it's not a DC actually. Okay. So now we can find out by using a cursor, we can find out how much output signal amplitude we are getting. Okay. So let's take a cursor one. Okay. So I will go to the right click, go to next Ymax value. Okay. So let me select the output signal first. Input signal is selected. So I will select the output signal. Now my output signal is selected, and I will go to next Ymax. Okay. So you can see here in the reading box, Y1, clear? I'm interested in a V out. Okay. So how much V out I am getting? I'm getting a 131.7 millivolt output. Clear? So output amplitude, I'm getting 131.70 millivolt. Okay, so And the input, we know that how much we have applied, that is a 1 millivolt. So gain will be V out divided by V in. So let me write it. Okay, so 131.70. I will use the text box. 1 minute. Let me take the text box. Okay, so my gain AV will be equal to, better I will use text box of this one. It will be more clear to you. Okay, AV will be equal to V peak divided by V out peak. Okay, V out peak divided by V in peak. Okay, so which is 130. How much? 131.70. Okay, millivolt divided by 1 millivolt. Okay, so you are getting a gain of 131.70. Okay, so I hope you understood. So this much gain we are getting here. 131.7 is the gain of this amplifier. This is without feedback. We haven't connected, applied the some of the portion of the output to the input. Okay, we are not getting any output signal to the input. So it is without feedback circuit, and we are getting a gain of 131.70. So I hope you understood the MOSFET common source amplifier. This configuration we called open loop configuration. Okay, this is the open loop amplifier. This is the open loop amplifier. Okay, so now what is the problem with this using amplifier in an open loop configuration? Obviously, in very few application we use this in an open loop configuration, amplifier in an open loop configuration. Okay, so in most of the cases we use amplifier with a feedback. Okay, so already amplifier with a positive feedback we have studied in the last experiment, that is the oscillator. Okay, so oscillator we already know that it is a amplifier with a positive feedback. Okay, so that is the oscillator circuit. Okay, even for amplifier applications also, we don't use amplifier in open loop configuration. The reason is the commercial amplifiers are having a gain of this gain which we are having for this circuit 131, which is a very small. Okay, if you look at the commercial amplifiers, so you will find out commercial amplifiers are having open loop gain of more than 1 lakh. 1 lakh, I am saying 1 lakh. Okay, so open loop gain of more than 1 lakh. Okay, so what will happen? Even your input signal is very small, maybe even in a few microvolt or even a picovolt. Okay, so what will happen? The amplifier will saturate. What do you mean by saturate? V out will exceed above the VDD. V out will go because of the very large gain, 1 lakh gain. You can understand input signal will get multiplied with the 1 lakh. That is your V out. Okay. So what will happen in maximum cases, most of the cases, now V out will go beyond the VDD, and that is not possible. So what will happen? V out will clipped, because V out cannot go beyond VDD. There, V out cannot go above VDD and below the ground. Okay, so that's the restriction. Clear? So what will happen? V out will get distorted. You will get a clipping of the V out signal. Okay, that we call the saturation. Amplifier gets saturated. So that's the reason we don't use amplifier in a open loop configuration. Clear? Because of very large gain. Clear? V out will get saturated. Okay. So what is the solution then? So we have to reduce the gain of the amplifier to our desired value, to our required value. We should have a control over the gain of the amplifier. Okay. And that the gain value we can control by providing a feedback, but not a positive feedback, a negative feedback. Okay, because we want to reduce the gain. We don't want to increase the gain. Clear? Your oscillator. In oscillator, we want to increase the signal, whereas in a amplifier applications, we want to reduce the open loop gain of the amplifier to our desired value. Okay. Say for example, I have an application and I want my amplifier should have a gain of 1000 only. Okay. I want my amplifier should have a gain of 1000. So open loop gain is 1 lakh. So I have to apply a negative feedback such that my overall gain with feedback, with negative feedback should be 1000 only, not 1 lakh. Okay, so that's the reason we don't use the open loop amplifiers in open loop configuration. Clear? And we use the negative feedback to get our desired gain value. Okay. So I hope you understood what is the importance of the negative feedback in amplifiers and why we have to do it. Okay, why we have to go for a negative feedback in amplifiers. Okay, so now there are in theory we will study it in a detail, different types of feedback types and the topologies. Okay. So very quickly, just I will name these feedback topologies. So depending on the which type of feedback you are in a negative feedback, we are talking about the negative feedback only, not positive feedback. Okay, about positive feedback we talk in the oscillator. Okay, now there are 4 types of negative feedback we can apply. Okay, so first one is a voltage series negative feedback, then voltage shunt negative feedback, then current series negative feedback, and current shunt negative feedback. Okay, so negative feedback has these 4 types. Okay, so out of these, the simplest and the first one, voltage series negative feedback, we are going to experiment in this experiment. Okay, so let's see how we can provide, we will use the same amplifier and we will provide a voltage series negative feedback. So let me go to the next circuit. Okay, so let me remove this. Okay, so you can see here, this is the feedback circuit I have used. Okay, just voltage divider feedback circuit, resistive feedback circuit I am using. Okay, and what I am doing, I am a fraction of V out. What this voltage divider circuit will provide me, it will provide me a fraction of the V out, some part of the V out. Okay, which is a voltage. Obviously, voltage I am sensing at the output. I am sensing the voltage. That's why it's a voltage feedback topology. Okay, and this voltage I am applying in series. You can see here this voltage, feedback voltage. Okay, I am applying in series with my input signal. I am adding this uh, fraction of the output voltage, okay, in series with the my input signal Vin, okay. So instead of saying adding, I will say subtracting because it's a negative feedback, okay. So that's why this topology is known as a voltage series feedback, because what I am sensing at the output, I am sensing voltage at the output. That's why it's a voltage feedback topology. And that voltage I am adding, or what we can say subtracting, not adding. Basically, we will say adding, we don't say subtracting, clear? So I'm adding in series with the input signal. Yes, that's why it's a voltage series feedback topology. Okay. Okay, in theory, we will study all these four types in a detail. Okay, so now let's take, and obviously, I already told you why we are using a negative feedback to reduce the gain to the some lower value, to our desired low value. Okay, let me clear the drawings. And this feedback factor, this is the beta, you can see here. This feedback factor is denoted as a beta, okay, and which from this circuit is nothing but the factor or a fraction R2 divided by R1 plus R2. It's a simple voltage divider network, okay. So this is my feedback fraction or feedback factor, okay, R2 divided by R1 plus R2. And now what is our gain? With this negative feedback, our gain, that is denoted as AVF, feedback voltage gain, okay, feedback voltage gain, and that will be the AV means open loop voltage gain, which we have calculated in the previous circuit, divided by 1 plus AV into beta. Okay, so this is the expression for the feedback voltage gain, clear? The new voltage gain value with feedback, okay. So that is AV divided by 1 plus AV into beta. Here AV is a open loop voltage gain, clear? So let's check out, again run a simulation and we will find out how much is the value. Okay, so let's run the transient analysis again. I have to clear all this drawing. Okay, same, I'm keeping same start time, end time, input and output. I want to observe and I will run the simulation. Yes. Now this is the simulation result we are getting after adding a negative feedback. Okay. Now let's cursor measure how much using again cursor 1. Okay, so let me select the output signal first, and then let's go to next Y max value. So I'm getting a 4.79 millivolt. Okay, so here I'm getting a V out 4.79. I will say 4.8 millivolt. Okay, so let me note it down. So here I'm getting EVF equal to 4. So that is a V out I am getting basically. That is itself is a because input is a 1 millivolt. So 4.8 divided by 4.8 millivolt divided by 1 millivolt. So AVF I am getting 4.8 here. Okay. So after with a negative feedback, I'm getting a gain of 4.8. And what was our earlier feedback? Earlier without feedback value, that is that we have removed. Okay, so I think 131. Okay, AV is 131, around 131.7, I think we got 170. So now you can check out our gain is reduced by reduced to a lower value, 4.8. Okay, and we can control how much gain we can calculate, how much beta we should provide, and accordingly, clear. We can say for example, I want gain of 50. So I have to calculate how much beta I require, and beta I can control by selecting the R1 and R2 values. Okay. So suppose I want gain of a 50. So I have to find out how much beta I required, feedback fraction I required. Okay. And then by choosing the appropriate values of R1 and R2, I can select that appropriate feedback fraction or the factor, and I will get uh, gain of 50. That's way we can do it. Okay, so for a gain of 50, just you have to change the values of R1 and R2, and you will get a gain of 50. So I hope you understood. This is the way we have to perform this experiment. Okay, now you can verify theoretically whether really you are getting the almost same value which we got practically. So EV is you can keep these things. You can calculate the beta. R2 is known, R1 is known. You can calculate the beta. Okay, AB is known, that is 131.7, and you can find out theoretically how much gain you are getting, feedback gain you are getting. Okay, that must be close to 4.8. Yes, obviously, practical and theoretical values should be close to each other. So that you have to do in a write-up. Okay, in a write-up you have to also calculate the theoretical value of the feedback gain. Okay, so I hope you understood this experiment. So this is the way we have to perform this experiment. You have to attach a screenshot of both the figures, without feedback, with feedback. Okay, both the circuits as well as both the simulation results. Okay, without feedback simulation results, with feedback simulation results, by keeping proper cursor at proper locations, clear, so that in the window, in the reading window, your gain should be visible, clear. V out should be visible. That V out itself is a gain, so that should be visible. Okay, even same thing you can perform by running the AC analysis also, AC sweep also, clear. So instead of transient, you can run a AC sweep also, and from that also you can get the same value. Okay, let me very quickly show you. Okay, so I have to clear the. Let me erase this some drawings. Okay, so let me select the AC sweep. Output V out. Okay, so this is your magnitude plot, and lower one is your phase plot. So we are for gain, we required a magnitude plot. So just add a cursor. You should get a 4.8 around. This is your AVF 4.8. So that much we should get. Okay, so let me add a cursor to this top one. Yes. So cursor 2 I am using. You can see I'm getting you can check it at 1 kilohertz, because our input signal frequency, I will set it to the 1 kilohertz, because for transient our frequency was 1 kilohertz. So from the this response also we have to check at 1 kilohertz. Set Y value to 1000, that means 1 kilohertz. What happened? X1, X2. Okay, so let's set Y value in this direction, 1000. Why it is not going to the, not Y value, X value I have to set. What I'm doing? Okay, because frequency I have to set, X value, 1000. Okay. So X2 is 1K and you can see Y2, that is my output magnitude, which is equal to the gain. I'm getting 4.79. So exactly same which I got by running the transient analysis, I got by running the EC analysis also, 4.79. Just rounded to the 4.8. Okay, so I hope you understood how we did the find out the gain by transient analysis as well as the EC analysis. Okay, so the same thing by connecting CRO also you can check out. Okay, so I hope you understood. So we will stop here.